Hi, I'm John Paul Raj, and I'm on a mission to make the learning of math fun. So if you're new to this channel, please do consider subscribing. This is part 3 of continuous functions. And on this video, we're going to talk about types of discontinuity. Let's start. When we look at a graph like 1 over x, the reciprocal function, in order to draw or sketch the graph of a reciprocal function, the first piece, then you lift the pen to draw the second part or the second piece of this function. And therefore, we say that this graph is not continuous. But should we call it a discontinuous function? Some textbooks would argue, they would say that, well, at x is equal to 0, yes, there is a discontinuity because there's a vertical asymptote, but x equals 0 is not part of the domain of a function like this. So why are we even talking about continuity or not continuity for something which is not even part of the domain? Interesting argument, isn't it? I'd like to know your thoughts about this. When something is not even part of the domain, should we even talk about the continuity or the discontinuity of the function at a point which is not even part of the domain? Let me know in the comments below what you think. And in order to avoid that confusion, many textbooks rather use the word point of discontinuity. So instead of saying that 1 over x is a function that is not continuous, they'd say that x equals 0 does not belong to the domain. So x equals 0 is a point of discontinuity for this function. Now, there are 3 different types of discontinuities, all right? So let's take one at a time. If you have a function, let me just bring in my coordinate plane there. Here you go, x-axis and y-axis. Let me label this x and y. And let's say we had a function something like this, okay? There's a function and this is the other part of that function. All right, so it's going this way and this way. Can you guys see this? And let's call that point A. So what's happening? Let's say that's your f of A. So as x approaches A from the left-hand side, as x approaches A, the values of the function, look at the values of the function, they are approaching a value, let's call that value k, all right? So the values of the function are approaching k, they're not equal to k because at A, what's happening at A? At A, the value of the function is f of A. There is a hole here, but the value of the function is f of A at x equals A. And then on the right-hand side, okay, on the right-hand side, what do we see as x approaches A from the right-hand side? The values of the function are approaching A, all right? So we can write down that limit as x approaches A from the left-hand side, f of x is equal to k. Remember, it's not equal. That's okay for limits. If you've not seen my video on limits, I'm going to link that video. Go and take a look at it, okay? The limit of the function, the left-hand limit, okay? The left-hand limit at x equals A is k. The right-hand limit, however, as x approaches A from the right-hand side, f of x is equal to f of A. So both the left-hand limit and the right-hand limit exist, but they're not equal, all right? As such, we say that the limit does not exist because for the limit to exist, both the left-hand limit and the right-hand limit must exist. This scenario, this case where the left-hand limit and the right-hand limit are not equal, they exist, but they're not equal, is what we call a jump discontinuity. A jump discontinuity occurs at a point A where the left-hand limit is not equal to the right-hand limit. They both exist, but they're not equal. So that's the first kind of discontinuity. Let's make a note of it, all right? So the first one is called jump discontinuity. And it occurs because the left-hand limit is not equal to the right-hand limit. All right? The second type of discontinuity, let's look at another example and let's just visualize that first, all right? I'd really like visualizing. It helps to understand better. Okay, so let me draw a grid. And this time, can you guys see this? Let me just label this x and y quickly. All right. Again, let's take A as a point that we want to consider the continuity or the discontinuity. All right. And let me draw the function like this. All right. So as you can see that there is a hole at x equals A. That means that if that is f of A, fa is not defined, okay? The function value is not defined at A, fa, I'll write down here, fa, not defined. That's the meaning of whole, right? I'll just write that thing also down here. There's a whole, and FA is not defined because primarily A is also not part of the domain. Okay, so A is not part of the domain, FA is not part of the range, and there's a hole in the graph. So as x approaches A from the left-hand side, what's going on to the function? The function values come closer and closer to f of A, but they are not equal to f of A. Why? Because FA is not defined, FA is not part of the range. So we can say that the left-hand limit as x approaches A from the left-hand side, f of x is equal to f of A. Okay, the value of the limit is not equal to the value of the function. That's okay. The limit exists and the left-hand limit is equal to f of A. And what is happening as x approaches A from the right-hand side? As x approaches A from the right-hand side, the values of the function are coming closer and closer again to f of A. So the left-hand limit and the right-hand limit are both equal to f of A. So I'm going to write down limit as x approaches A from the right-hand side, f of x is also equal. They both are equal to f of A. But the only thing is that f of A is not defined. This scenario is referred to as a removable discontinuity. Okay, so I'm just going to write it down here in our notes. The second type of discontinuity is called a removable discontinuity. And that is when left-hand limit is equal to the right-hand limit, but f of A does not exist. So two types of discontinuities we've seen. Jump discontinuity occurs when the left-hand limit and the right-hand limit both exist, but they're not equal. The second type of discontinuity we've seen is when the left-hand limit and the right-hand limit both exist and are equal, but the function is not defined. And the third type of discontinuity is this example that we saw at the start of the video, right? So what is happening at x equals 0 if that were our A? Okay, let's call A is equal to x, which is at 0. Here we have a vertical asymptote. What's happening? Well, the limit as x approaches 0 from the left-hand side or from the right-hand side does not exist, becomes too large. And remember, we don't want to use the word infinity, all right? The limit does not exist. That means we say both the left-hand limit and right-hand limit does not exist. So this is a case which we have called a vertical asymptote. Some textbooks use the word infinite discontinuity. I personally don't like to use that word, infinite discontinuity. We'd rather say the third type of discontinuity is where the function has a vertical asymptote, which means left-hand limit, I'm running out of space here. Can you guys see? All right, vertical asymptote, the left-hand limit and right-hand limit do not exist. So these are the three types of discontinuities, all right? Jump discontinuity, where the left-hand limit is not equal to the right-hand limit. Removable discontinuity, where the left-hand limit and the right-hand limit exist and they are equal, but the function is not defined at that point. And a vertical asymptote, where the left-hand limit and the right-hand limit does not exist, meaning there is a vertical asymptote. The values of the function become too large. In the next video, we will look at examples and analyze whether a function has a discontinuity and the type of discontinuity it has at that point. See you there.